So chapter one begins with defining a graph as um, G equals an ordered pair of V and E. So V stands for the set of vertices that a graph would have, and E stands for the set of edges that a graph would have. So real quick, I'm going to draw kind of a pretty simple graph. Let's say this is A, B, C, D, and E. So the only restriction that graphs have is that the set of vertices can't be empty. You're allowed to have an empty set of edges. So for instance, what would be in my vertex set here for this graph, to describe this graph would be A, B, C, D, and E. And my set of edges are the lines connecting the vertices. So since this is an undirected graph, this would be A, C, well, AC, where A is one endpoint and C is the other endpoint. I'm not going to list them all because I ran out of room. But does this make sense so far? How do I clear this? Okay, I think I'll have to use this program. Uh, there will be 0-1 questions related to sections 10.1 of Rosen, 10.2, 10.3. Okay, I'll just go over in order. So we're currently on 10.1. So after they define uh how a graph is defined, they go into the types of graphs that exist. So I like to split these up into okay, this is a really weird program. Undirected and directed graphs. So first we'll go over undirected graphs. So in undirected graphs, you have a simple graph. You have a multi-graph. Yeah, a multi-graph. And you have a pseudograph. So a simple graph kind of looks like okay. Interesting. Oh, I see. All right. A simple graph looks like this. You have your vertices, and you have only one line connecting each node. And you don't have any loops in the graph. A multi-graph would look like this, where between two nodes, you might have something that looks like this. So this is one edge connecting these two vertices, and this is another edge. So there are multiple ways to get from this vertex to this vertex using these two edges. And then you have the pseudograph, which is just very similar to the multi-graph. You're allowed to have multiple edges between any 2 points. And you also have what's called a loop, where one vertex has an edge that connects it to itself like this. And you could have it for any number of vertices, but basically a pseudograph says that this is allowed. Does that make sense so far? All right. I'll just erase these for now. And then after you have all the types of undirected graphs, you'll have a different classification. Yes? You want to do example questions from each section? Oh. I'll just quickly go over the definition first and then go over some questions from 10.1. Yeah, so these are the directed graphs. So for directed graphs, we have something similar. We also have a simple graph for the directed graphs, a multi-graph, and a mixed graph. So the simple graph, very similar to the what you saw with the undirected graph. But instead you have a directed edge that has a direction. So this has to be an ordered pair. So if this is vertex U and this is vertex V, you have to go from U to V. And every edge in a directed graph, in a simple directed graph, has to have the direction. A multi-graph is similar to the undirected graph, where the underlying graph looks just like a simple undirected graph. So you have like multiple edges going from one vertex to another, but they have to be in the same direction. So this counts here, but yeah, they have to be in the same direction. And then you have a mixed graph, which allows a mix of directed and undirected edges. So something like this, and you're also allowed loops, where the loops might have direction as well. Does that make sense so far? All right. Then I'll quickly go over some questions from Rosen. I have
Wait,
the textbook.
just to be
Yeah?
sure, for the directed multigraph directed, the direction of each of the edges has to be from the same terminal point to the beginning from terminal point?
Yeah, I think so. Let me recheck the definition real quick. But I think it only counts if they're in the same direction. Otherwise, they're counted as two different edges. But let me recheck what's going on here. So directed multiple edges allowed. So direct multigraphs, each associated to an ordered pair. Okay, yeah. So it's correct in that this counts here. This would be a directed multigraph. But if this was going in the other direction, I don't think it would be, because this is a different kind of edge than this one. Since these are ordered pairs, because when you have U comma V, that's not the same as saying V comma U. Does that make sense?
Yes.
Okay. Then I'll go over one of the questions from 10.1. You guys can choose. I don't know if my edition of the textbook is different from yours, but I guess whichever exercise you guys want to go over, just mention it. Otherwise I'll pick one of the homework questions that he gave you. Let me see. Okay, so he gave you 1, 3, 4, 5, 6, 7, 8, 9. 1, 3. Okay, we could go over exercises 3 to 9. Section 10.1, page. Oh yeah, it's I am on the right page. I think my textbook looks a little different from yours. It might be a different edition. 773 to 76, which is I mean page 673 to 676 is kind of what I just went over, which was the types of graphs, simple graphs, multi-graphs, pseudographs, and non-directed graphs, and what loops are, basically. So yeah, I'll go over questions 3 to 9. So 3, since there are no directional arrows here.
I think you're still sharing the drawing.
Okay, shoot. All right, sorry. Let me change that. Embarrassing. All right. All right. Okay, can you see this?
Yep, you can see it.
All right, thanks. Okay,
And if
so
you want to
questions.
draw on it, there should be a little annotate
Yeah,
feature. Just looking at
annotate. Yeah. All right. So 3. You can see that these edges don't have directionals like this. So this would be a simple undirected graph. It has no directed edges, so they're undirected, and you don't see multiple edges connecting two things or two vertices. You also don't see something that looks like this, so that means there are no loops. All right. So a harder problem, we could look at 5. So 5, you can see that it has no directions, so these are undirected. You have multiple edges connecting A and B, and you can see that at vertex A, you have a loop, vertex B, you have a loop, and D, you have a loop. So that means that this would be a pseudograph, because pseudographs, you're allowed to have multiple edges, but also you're allowed to have loops. As opposed to graph 6, you see this has no loops, but it does have multiple edges connecting B and D and A and C. So this would just be a simple, wait, not simple. This would just be an undirected multi-graph. And then when you have something more complicated that looks like 9, let me just clear this. So 9 has directions. It also has, as you can see here, a loop. So that means this would be a pseudograph, because you're allowed to have loops in a pseudograph. Well, not a pseudograph. This is a mixed graph, sorry. So you have loops in a directed mixed graph. All right. Is that clear so far? If so, I can just move on to 10.2. Or
So
is there a yeah?
7 and 9 are mixed, and 8 is multigraph.
8 is also mixed. I think with mixed graphs, you that's the only time you're allowed to have a loop. But let me check again.
Oh, okay.
Okay, so mixed. Oh, directed. Yeah, you're allowed to have. Sorry, I messed up. Yeah, thanks. So let me see. So 7 is a multigraph. 8 is a multigraph as well. Let me look at 9. I think 9 is also a multigraph because I don't see a mix of directed and undirected edges. Sorry, that was my bad. But yes, in multigraphs for directed graphs, you're allowed to have loops. All right, then I'll move on to 10.2. Okay, so 10.2.
Sorry, but didn't you say for multigraph for directed, it has to be the edges has to be from the same direction?
Yes.
But there's like
for let's see, for directed graphs, you're only allowed to have a loop in multigraphs. So 7 has a loop at C. and E. So even though at C and D, you have one loop that goes this way, one edge that goes this way and one edge that goes this way, this would still be a multi-graph because you have a loop at C and a loop at E. Does that make sense? All right, then I'll just move on to 10.2. So 10.2 is talking about, let's see, I'll change to, change to this instead, right? And this one I can toss. So 10.2 is talking about how to tell, it's kind of trying to describe how vertices and edges interact with each other. So let's say I have a graph that looks like this. We're gonna work with undirected graphs for now. So this is A, B, C, D, and E. So in 10.2, it mentions that two vertices are considered adjacent if they're connected by an edge. Okay. So for instance, A and B, let me use a different color. A and B are adjacent because they're endpoints of the same edge. B and E are adjacent because they're endpoints of the same edge, but we wouldn't consider A and E to be adjacent. We also describe edges, how they interact with vertices. So this edge here would be considered incident with A and B because A and B are its endpoints. We wouldn't consider this edge to be incident with E because E is not one of its endpoints. Let's see. Expanding on the definition of adjacent, we also want to describe, let's say for a given vertex B, we want to talk about all the vertices that B is adjacent to. We would call this N of B. So N is just N of B is just the neighborhood of B. So if we describe the neighborhood of B, we would list, it's a set of all the vertices that it's adjacent to, so A and E. We can also extend this definition to a set of vertices. Let's say I want to describe the neighborhood of this set of vertices, A, B, and D. And I want to call this set, let's say, set X, capital X. So then I would say that the neighborhood of this set X is the union of all the vertices that each one is adjacent to. So let's say A is adjacent to B, so B is in there. B is adjacent to A and E, so these are in there. And D is adjacent to C and B. So this would be the neighborhood of this set X. That makes sense so far? Okay. So next, we want to talk about how many, extending from the neighborhood, we also want to talk about the degree of a vertex. So the degree of a vertex, let's say vertex B again. So the degree of B would just be the number of how many edges come out of it. So we can see here that B has one edge here coming out of it, or that it's the endpoint of. B has one edge here that it's the endpoint of, and one here that it's the endpoint of. So that means the degree of B is equal to 3. A cool, some further definitions. If I have a pseudograph, let me draw a pseudograph. Well, let me just add a loop to A here. Well, not A. If I added loop, let me use a different color. Let's see. If I add a loop to B that looks like this loop contributes twice to my degree. So this is my edge that's incident with B. This is my edge that's incident with B, and this is an edge incident with B. This is also an edge incident with B, but it counts as 2 edges. So this, if I add a loop to B, would become 5. That makes sense so far? So if a degree of a vertex is 0, let's say I add another vertex to this graph, and I call it F. The degree of F is 0. So that means it's isolated from the rest of the graph because there are no edges coming out of it to connect it to any other vertex, right? So a cool thing about the degree of vertices in the graph is we have the handshake theorem. Let me just write it out real quick. So the handshake theorem says that, let me, hold on. So what this says is that if I have a graph, G equals V of E, V comma E, that has, let's say, an M number of edges in the graph, then I'm guaranteed that twice that number is equal to the sum of the degrees of all the vertices in the graph. Yeah, so basically, this kind of makes sense, right? Because if I have 2 vertices and I have one edge connecting them, the degree of this vertex, let's call it U, is equal to 1. And this one also, if I call this V, the degree of V is also equal to 1. So if I add these two, if I sum this up, this would be 1 plus 1, which is 2. But I only have one edge here, right? But this is because that edge contributes twice because it has 2 endpoints. So it contributes a degree here, and it contributes a degree here. So every edge in a graph will contribute twice its number, basically. Let's see. And I think this, let's see. So some cool properties that come from this is if you have an odd number of, or if you have vertices of odd degree, you can't have an odd number of vertices with odd degree because then you have an odd times an odd, which makes it odd. But you're not allowed to have that because this says that when you sum up the degree of all the vertices in the graph, it has to be an even number. So you might encounter some problems. Let me use an example from the textbook. Hold on. Okay, 10.2. Let's see a problem that relates to this is, okay, so number 5 here, that says, can a simple graph exist with 15 vertices, each of degree 5? The answer would be no, because if you have 15 vertices of degree 5, that means you have 15 times 5, because each vertex has degree 5. So when you add them all together, you're basically multiplying 15 by 5, which is 75. But then the sum of this is odd, and the handshake theorem says you're not allowed to have that. So typically questions related to the handshake theorem mostly ask something like this, where usually you can show that it's not possible because it has to be even. Do you want to do another question related to the handshake theorem, or I might move on to let's see. I'll move on to like directed edges. Okay, then I'll just move on. Okay, let's see here. Where are my layers? I think my layers so strange. I'll just start a new file. Okay. So we have a separate definition for graphs with directed edges. So for graphs with directed edges, let's make this a simpler graph. So this is A, B, C, you have this, and I have this. So in the graph with directed edges, we call, if we have an edge going from A to B, we say that we say that A is adjacent to B, but B is adjacent from A. And we call A the initial vertex, and we call B the terminal vertex, or the end vertex. But if we have something like a loop like this, then C is both the initial and the terminal vertex. We describe the degree of a vertex in the directed graph separately, depending on which direction the edge is going. So let's say I have something like this. If I have multiple edges, if I have multiple edges going to be like this, where B is the terminal vertex, we would call this the in degree of B. And I think that you would call this degree plus B. So since there are 2 going into B, this would be 2. We also have something called the out degree. A, let's use A instead. Degree minus A. This minus usually goes above. Same with the in degree. So the out degree of A, since there's one edge coming out of it, this would be 1. Does that make sense so far? And a loop contributes 1 to both. So C has a loop that goes to itself. So since C is both the terminal and the initial vertex, this loop adds 1 to its in degree, and it adds 1 to its out degree. And a theorem that comes from this is that the sum of your in degree of a vertex of any vertex in a graph, in a directed graph, should be equal to the sum of the out degree of all the vertices in the graph. To like kind of illustrate that this is true. Oh, and this is also equal to the number of edges in the graph. This definition only applies to directed graphs though. And to kind of see that this is true, if I have a very simple example, one edge that goes from U to V, this contributes, each edge contributes an out degree of 1, and each edge contributes an out degree, an in degree of 1. So they contribute an equal number to both because it has an initial and a terminal. Does that make sense so far? Okay.
Can you
So-
explain the theorem again?
Oh, the theorem?
Yeah.
Basically, let me hold on. Let me
So
draw a
Z-
better graph.
So in theorem are both of those V's?
So let's say my graph is hold on, V comma E. So when I say this, that's basically saying for every vertex in this set V. So if I sum up the out degree of all the vertices in this graph, it should be equal to all the out degree, or the sum of all the out degrees of the vertices in the map, the graph. So let me draw a directed graph here. So you can see that for this edge contributes an out degree of 1 here, and it contributes an in degree here of 1. This edge here contributes an out degree of 1 here, and it contributes an in degree of 1 here. And this edge going downwards contributes an out degree of 1 here, and an in degree of 1 here. So this and these two are my in degrees. This and this, let me use a different color actually. This, this, and this are my out degrees. So you can see that for this graph, it's pretty apparent. It's pretty apparent that your out degrees are equal to your in degrees. Does that make sense?
Okay, I see what you mean now. So this is talking about the entire graph, not just like one or two vertices.
No, it's talking about the entire graph.
Okay.
Okay, so moving on, the chapter goes on to talk about special kind of graphs that you'll see. I'll just erase all this. Okay, you don't want to be erased. Okay. So the next part is about special graphs you'll see. The first kind are complete graphs, which are denoted K of n. So n usually just denotes the number of nodes or vertices in the graph. So these are complete graphs, which means that you'll have an edge between every distinct pair of vertices. So this is K of 1. So this one doesn't have a pair of vertices, so it's just a single dot. K of 2 looks like this, where you have two vertices and you have a line connecting them. K of 3 is a triangle. So between every pair, you have an edge connecting them. And then for K of 4, you have four vertices. And if I like very systematically draw an edge going from one vertice to another and make sure I like connect every distinct pair, it ends up looking like this. So you can just do this for any number of vertices you put down. You'll create a complete graph. Yeah. So do you guys want me to go over all the special kinds of graphs, or because you can kind of take a look at them, and I don't think a lot of them tend to come up besides cycle and the complete yeah, I think besides complete graphs and cycle graphs, it's not the other kind of graphs don't tend to come up as often. Otherwise I can move on to like the next part of this section.
Can you go over really quick Q graphs?
Okay. So Q graphs are kind of let's see. Right. Q graphs are denoted Q sub n. So what this is representing are 2 to the n bit strings of length n, where adjacent vertices differ in like 1 bit position. Let me quickly write it out. So this is Q of 1. So this vertex is labeled 0, and this vertex is labeled 1. So since this is Q of 1, you have 2 to the 1 2 to the 1 bit strings, which is you only have 2 bit strings and they're of length 1. So that means single digits, 0 and 1. And you have for each bit string that differs in 1 place. So this differs by 1 in 1 place here, as in the only place that it has. These two have to be adjacent to each other. So that means you have to draw an edge connecting them. Q2 has 2 to the 2 number of bit strings, which is 4. That means you have to draw 4 nodes here. So these 4 nodes, each node represents a bit string of length 2. So if I call this one 0, 0, and I call this one 0, 1, and I call this one 1, 0, and 1, 1, the ones that have to be connected to each other are the ones that differ by 1 in only 1 place. So since this one differs by 1 in the ones place ish, these two have to be adjacent. So that means I have to draw an edge connecting them. This number and this number differ by 1 here. So I connect these two. This number and 10 differ in the ones place. So I have to draw an edge connecting that. And 10 and 0, 0 differ by 1 in the tens place. So I have to, I call it the tens place, but it's not actually the tens place. So I have to draw an edge here. But I can't draw an edge connecting 10 and 0, 1 because they differ by 1 in 2 places. So I leave that alone. Does that make sense so far?
Yes.
Yeah. I could still draw Q3, but I kind of don't want to because that has 8 nodes. But basically you follow the same kind of process where you have to draw, since this is Q3, you have 2 to the 3, which is equal to 8. So you have to draw 8 nodes, something like this. And then you have to label the nodes as like 0, 0, 0, 0, 0, 1. So 0, 0, 0, and 0, 0, 1. Since they differ by 1 in 1 place, you have to connect these two. You basically kind of like have to do that when you write out all the numbers for this.
Okay.
Yeah.
So just
Yes.
to summarize, so like K graphs are like complete graphs, all the vertices are connected. Cycle graphs are more of like are similar to K graphs. Like
Mhm.
all of the vertices are connected there, and
Yeah.
then wheel
Not all
graph.
the vertices are connected. Let me go over
Like the two adjacent vertices are connected.
yeah, adjacent you can't you're basically trying to create a circuit or a cycle.
A circle.
A cycle. Let me try to erase this. Oh, it doesn't want to erase. Okay. I'll go over the cycles because I think those tend to come up as well. So Cn, your n has to be greater than or equal to 3. You have a set of vertices with edges with us. You have a set of vertices. So let's say v1, v2 up until vn. And the way these vertices have to be connected is these are the edges that have to connect these vertices, where you have to have v1 comma v2, where v2 is like adjacent to v1. And then your next edge has to be the edge connecting v2 and v3. And so on until you reach n minus 1, vn. And then the last edge is the one connecting vn back to v1. Does that make sense? This is usually how cycles work. So if my n is 3, so let's say my n is 3, but let's call this v1, v2, and v3. I follow this pattern where I connect 1 to 2, then I connect 2 to 3, and then since 3 is my n, I connect 3 back to 1. Yeah. So that's basically how cycles work. I'll move on now to bipartite graphs. Or oh, he mentioned Hall's theorem, Hall's marriage theorem. I'll quickly go over bipartite graphs first, so that there's context for Hall's theorem. So a simple graph is bipartite if so this is for simple graphs, v comma e. So this is bipartite if v can be split up into two disjoint sets, v1 and v2. So that every edge that connects a vertex in v1, every edge connects a vertex in v1 to a vertex in v2. So let me draw an example. So let's say this is my graph. So this is my collection of vertices B. But let's say I split this up into disjoint set v1 and v2. So this would be a bipartite graph if every edge connects v1, a vertex in v1 to a vertex in v2 like this. It doesn't have to be all the vertices, but basically the endpoint of each edge has to be one vertex in v1, and the other endpoint has to be a vertex in v2. So what would make this not a bipartite graph is if I did this. Now this is not a bipartite graph because my edge is now connecting two vertices in v2, which means that it's not following my rule where I split this up into two disjoint sets. Likewise, this would make it not a bipartite graph. Does that make sense? All right. So a theorem for this is that you can figure out if a simple graph is bipartite if it's possible to color every vertex one of two different colors so that two adjacent vertices are not the same color. So if I do this, I color this one this color, and then I color this one a different color, hopefully. So these two are adjacent, so they have to be different colors. And now this one is connected to a vertex here, so I have to color that one the same color as the other one I was using. And now the other thing I have to look out for is this vertex is connected to a vertex here. So since this red color is already being used on the left side, I have to use a blue color on the right side. So that's a different blue than I was using here. And then my last vertex, I can color anything I want because it's not adjacent to anything. So you can use this just to figure out if a simple graph is bipartite, because this kind of proves that it is bipartite according to a theorem in this chapter of Rosen. So for Hall's theorem, Hall's marriage theorem relates to bipartite graphs. So let me type it out. If I have a graph G V comma E that is bipartite, where V has been split, V has been bipartitioned into two sets, V1 and V2, where you have a complete matching from V1 with, let me just type this out first and then I'll explain it. From V1 to V2, then you have has a complete matching from V1 to V2 if and only if, interesting. If and only if this is the case. Let me write it out. The neighborhood of A, where A is all this for A is basically any subset of V1. So the neighborhood of any subset from V1 has to be greater than or equal to the size of that subset. So what this means is, so this graph has to be a complete matching. So that means every vertex from V1 has to be connected to every vertex in V2. So I will draw this out. So let these two, this one be my V1. This is my V2. So I have to draw a complete matching. So this goes to here, this goes to here, this goes to here, and this goes to here. And then this has to go to every vertex in V2 as well. So this is a complete matching. And it also looks very messy, I'm sorry. But basically, let's say there are 4 vertices here and 3 vertices here. So let's take any subset from V1. Let my subset be these two. So the size of this subset is 2. So that's my A size of that's my cardinality of A. So the cardinality of this subset is 2. The cardinality of my neighborhood of these two vertices, since each of these has to be adjacent to 4 vertices in V2, that means this one contributes a degree of 4. I mean, not a degree. Well, it is basically not a degree, sorry. Well, it is kind of the degree, yeah. So this one is basically adjacent to 4 vertices in V2 because it has to be a complete matching. And this one contributes adjacency of 4 as well. So that means you're guaranteed that the size of this has to be, the size of the neighborhood of this subset has to be greater than or equal to the size of the subset itself. And it holds true here because you have 8 and 2. Does that make sense? So I think a problem for this, let me go to the textbook. Sum of out degrees, out degrees. Where does it talk about Hall's theorem? I think this is Hall's theorem. Suppose there are 5 young women and 5 young men on an island. Each man is willing to marry some of the women on the island, and each woman is willing to marry any man who is willing to marry her. Suppose Sandeep is willing to marry Tina and Mandana. Wait, let me think. Is this Hall's theorem? Ah, here's Hall's theorem. Okay. There's an integer k. Oh, sorry. Would you want an re-explanation of Hall's theorem, or should I just try to solve a problem related to Hall's theorem, or would that help clear things up? Okay, then I'll work on a problem and try to explain how to use it. Okay. So there's an integer k such that every man on a desert island is willing to marry exactly k of the women on the island. Every woman on the island is willing to marry exactly k of the men. So since each man is willing to marry k of the women, each woman is willing to marry exactly k of the men. A man is willing to marry a woman if and only if she is willing to marry him. Show that it is possible to match the men and women on the island, so that everyone is matched with someone they are willing to marry. Okay, so Hall's theorem says that. Let me think. So I'll just use 3 as my k for now. So it's saying that a man is willing to marry if and only if she's willing to marry him. And it's possible to match the men and women so that everyone is matched with someone they're willing to marry. Let me think. This is kind of confusing. Okay, so I think because there's a certain integer k, it doesn't mean that there might be more than k men, or there might be more than k women. So the number of men on the island has to be greater than or equal to k. The number of women on the island. Actually, let me just copy paste this and solve it. Okay, interesting. All right. Okay. So what I can tell from this is that the number of men on the island has to be greater than or equal to k. and the number of women on the island has to be greater than or equal to K. Because it's saying K of the women and K of the men. If a man is willing to marry a woman, if and only if she is willing to marry him, let's say that the size of the subset of men is equal to K. So let, oh, okay. So let, interesting, okay. Sorry, I'm struggling a bit. Let let the subset of V1, I'll say V1 is the set of men. Let that be equal to let's say M1 up until MK. So K men altogether. Since the size of this set is equal to 6, I mean equal to, why did I say 6? It's equal to K. Hall's theorem guarantees that the number of possible matchings, the neighborhood of A, which is the number of possible pairings to the number of women, any number of the women is equal to, it has to be greater than or equal to K. So that it's possible to match the men and women on the island so that everyone is matched with someone they're willing to marry. So since it's greater than or equal to K, what we could have is, let me model this out for a bit. Suleiman, do you have any idea of how to go about solving this? So I don't waste everybody's time trying to figure it out.
So, what does the theorem say that Hall's theorem says? Okay, such that every man on yada. Also suppose that a man is willing to marry a woman if only if here show that it is possible to match the men and women match with someone they are willing to marry. Well, the worst, okay, so maybe it'll help you think about it for different types of K. So if K is 1, so every man wants to marry one woman.
Let's say there are more than one.
So like there's
So-
more men and women. So like this is men. 1, 2, 3, dot, dot, dot. And then the woman. Any integer K such that exactly K of the woman on the island and every woman K of the men. A man is willing to marry a woman if and only if she is willing to marry him. Show
Okay.
that it is possible to match the men and women on the island so that everyone is matched with someone they are willing to marry. Well, it doesn't tell us. Because if it's say K is like 2, so a man is only willing to marry 2 women, but if those 2 women aren't willing to marry him, then you can't. Hold on.
I think it only matters who the woman is willing to marry, because it says that the man is like cool with any woman so long as she wants to marry him. Oh wait, maybe what the question is saying is that every man and woman has a preference for of K, let's say K is 1, has a preference of K for the woman that he wants to marry. But
Oh, wait.
if
Oh,
she's
yeah.
willing to, if a woman is willing to also marry him, he's willing to marry her as well. I think is what the question is saying.
So in this case, a man's preference doesn't matter as long as they're equal amounts.
I think so.
So like, because in that case, then yeah, it's pretty simple to prove. Because say this man right here,
Mhm.
this woman prefers to marry this man. So under this condition, a man is willing to marry a woman if and only if she is willing to marry him. These two are a match.
Yeah.
Okay, so then in that case, as long as the number of men equals the number of women, then everyone is matched. Because every woman's
Okay.
going to have at least one preference, right? So like once the woman like say she says it's a preference, and if the man's there, then boom, they're a
Mhm.
match. Otherwise, she goes to her next preference, and then yeah.
Okay. I think the question is also saying that you just have to show that it's a possibility. Where so let's say the
Well, if there are
subset.
equal number of men and women, then it's always going to be possible to like make a matching for both
Mhm.
groups.
I mean, I'm pretty sure Rosen has like answers for this. It's a odd number, so I'll just look this up. Yeah, sorry for the delay. Let's see, 10.3.
2,
10.2,
10.2. What's the question? I'll
50 or 31. A model this with an undirected bipartite graph with an edge between a man and a woman if they are willing to marry each other. By Hall's theorem, it is enough to show that for every set S of women, the set NS of men willing to marry them has cardinality of at least S. Let M be the number of edges between S and neighborhood of S. Since every vertex in S has degree K, it follows that a number of edges M is equal to KS. Because there are edges incident to NS, it follows that. Sorry, I don't understand this either. Yeah, sorry for wasting time. I'll just move on. If you have time before the exam, I guess ask your professor about Hall's marriage theorem. I don't exactly, I understand the theorem, but I don't exactly understand this particular question. So yeah, but I'll just move on so we're not wasting more time. Simple subgraph, new graph, union of two simple. A bijection. Okay, yeah, I can explain the bijection. Let's see. Trash. Okay, so for graphs, bijections relate to isomorphisms. So let's say I have two different graphs that are isomorphic to each other. Like this. So this is G and this is H. So let's say I have two graphs. How can you tell that they're basically the same graph, but just translated with edges and vertices translated differently? To do this, you have to find a bijection basically between their vertices that have uh, or between their graph invariants. So what a bijection is basically a function that goes from a set A to set B, but it preserves the qualities in set A and set B. So one thing that a bijection needs is the set of the cardinality of A has to be equal to the cardinality of B. So we can see this in isomorphic graphs because for a very quick tell for isomorphism, or when it's not there, is when you have a different number of vertices and edges. So you see in these two graphs, this graph has 5 edges. This graph has 5 edges, and this graph has 5 vertices, and so does this. So a bijection for
I don't
these
think
two
we're
graphs.
seeing the same screen you're seeing. We're seeing something different.
Oh shoot, sorry. Okay, here. So these two graphs, G and H, are isomorphic to each other. So to prove this, what I can do is have a function that when I put in, let's say, vertices from the graph G, it'll output vertices in graph H that have the same qualities. So if I label this A, B, C, D, E, 1, 2, 3, 4, and 5. I can create my own function here. And if I write this out, I'll say that this function is defined this way. A function that goes from, wait, let me call this graph V1, E1, and this one would be V2, V2, E2. So I can define a bijective function that goes from G to H using the vertices where my function, when I put in A, it'll give me 1. As in, I'm connecting this vertex to this one. Because if these are isomorphic, if I use this as A, this should basically preserve the qualities in A. One quality in A, we call these graph invariants. So graph invariants are preserved by isomorphism. So one graph invariant is that G has 5 vertices, and each vertex has a degree of 2. So that's also a graph invariant, is the number of degrees for each vertex, as well as the number of total vertices and edges. So f of A should give me 1, f of B should give me 2, f of C should give me 3, f of D should give me 4, and f of E should give me 5. But that's basically what a bijection would be for 2 graphs that are isomorphic. If you have 2 graphs that are not isomorphic, you cannot create a bijection between them, because if I put in, let's say I erase this edge here, then my function here that used to be a bijection is no longer a bijection, because when I put in f of A, and if it gives me 1, it's not, it wouldn't work because 1 here has a degree of 1, while my original vertex A had a degree of 2. So this will not work anymore, because that's no longer a graph invariant basically changed in my function. Yeah. Does that make sense so far? Or should I explain more about bijections? Okay. Another thing about bijections is let me just erase this. So very quickly in discrete math before this class, you learned about functions. So you learned about injective functions and surjections, right? So an injective function is 1-to-1. So what that means is basically if I have 3 elements in my first set and 2 elements in my second set, a function that takes my first set to my second set has to they can't map to the same element basically. So this is a 1-to-1 function, as in my inputs. Oh wait, this is a 1-to-1 function. My inputs have to map to an output, but 2 of my inputs can't be mapped to the same output. So this would, so as an example, this would not be an injective function. On top of that, you also have surjective functions, which are onto. So an onto function basically just means your inputs, when they get mapped to the outputs, it has to cover all of the outputs. So all of the outputs just have to get mapped to. So this is onto because all of my outputs here have something mapping to it. So as an example, this would not be onto because there are not enough inputs to cover the outputs. A bijection is basically has both injection and surjectivity at the same time. So it has to be both 1-to-1 and onto. So what that means is two of the same inputs can't be mapped to the same output. On top of that, all the outputs have to get mapped to. So the only way we can have a bijection is when the number of inputs is equal to the number of outputs. That's basically the definition of a bijection. Yeah. If we're talking about bijection in relation to graphs, you're typically using them to prove isomorphism. Let me go to the textbook real quick. Let's see, representing graphs, isomorphic graphs. Let's see, which chapter is isomorphism? Okay, these are isomorphic graphs. Okay. So bijection in relation to graphs is typically used to prove whether 2 graphs are isomorphic. So if I look at this particular example, 38, if I can write a function that takes in any of the vertices, any of the vertices in the first graph, and can output a unique vertex in the second graph that preserves its graph invariance, then I can prove that it has an isomorphism. So for this one, you can see that these 2 are isomorphic because even though this one looks different, what I can do is I can take V1 and connect it to V2, and then take the next edge that connects V2 to V4 and lay it out flat as well. And then take the edge that connects V4 to V5 and lay it out flat as well. Same with the one that connects V5 to V3. So one thing to look for, since we're trying to create bijection, is we want to make sure that the number of edges and the number of vertices is equal in both graphs. So there are 5 vertices here and 5 in this edges here. There are also 5 vertices here and 5 edges here. So one thing I can start with is, since V1 starts my graph here, I can say that when I put in U1 into my function, it should give me V1. That means whatever qualities U1 has, because I'm trying to prove isomorphism, V1 should also have them. That means that the edge that connects U1 to the next node here should also tell me what the next the next vertex that connects V1 should be. Since we have an edge that connects U1 to U2, since U1 is giving me V1 here, that means that in order to prove that this is isomorphic, the endpoint for these edges should, when I put them into the function, they should give me the same vertex here. So that means if U1 gives me V1, then U2, when I put that in, should give me V2. And this is because if U2 is the endpoint of this edge, I want this to be the same for V2. As in, I want V2 to also be the vertex adjacent to V1, because U2 is adjacent to U1. Does that make sense? I'm kind of yeah. So I just keep doing this basically, since U2 is adjacent to U3 next. Then I just use that and I connect it to this one. So that's when I input U3, I want it to give me basically the next vertex that's adjacent to V2, which is V4. So it's basically, you're trying to create a relation between the vertices in one graph, so that when you put them in, it should give you a vertex that is similar to the similar in the second graph. So if this is like basically going in sequence, then the next thing in the sequence should relate to the vertices here as well. That's like broadly what you're going to use bijection for in relation to graphs. I hope that made more sense.
So you see how U3 and V4 are not the same number? Is that okay?
Yeah, that's okay. The more important thing is that this line segment that connects U2 and U3,
Yeah.
that's telling you that basically, since you already did this line segment, or this edge, you want to start talking about the next edge. So this is like the only possibility that you can go to. This is just like how the vertices are numbered in the second graph. It doesn't relate to like the first graph at all.
Okay, so these two graphs now, they're both isomorphic and they both pass the bijection.
Yeah, if you finish writing out this entire function, which is just U2 takes you to V2. When you put in U4, it should give you V5. U5 should give you V3. So once you finish writing that out, that's your bijection that proves isomorphism.
Oh, so you have to prove bijection in order to prove isomorphism?
Yeah, you have to find a bijection from one graph to the other in order to prove isomorphism in the first place.
Oh, okay, makes sense.
Yeah. But these two graphs were already isomorphic. It's just sometimes you have to move the graph around to see that it's isomorphic.
Got it.
For instance, I'm going to clear this. these two graphs are actually isomorphic as well. It's just hard to tell that they are. So if I move V2 down here, this will give me something that looks like this, I think. V2, V5, V4. And then V4, let me think. V4, V1, and V3.
So for
So if I move,
complicated questions like these, we have to like play around with the angles like this and like keep drawing until we figure something out.
it's good to like get an eye for how to move these graphs around, because sometimes at first glance, they don't look isomorphic. But then
Right.
once you move the graph around a bit, you'll see that it is isomorphic.
So the only way to find a bijection is to move it around like this. There's no like algorithm or.
There are some things that can tell you if two graphs are isomorphic. One thing is like degrees. So this has the same number of vertices, same number of edges. Each vertex has a degree of 2, so that's like a good sign that it might be isomorphic. But these can only like give you like kind of clues that they are isomorphic. I think in a future section, it'll tell you that it'll give you another graph invariant that is preserved by isomorphism, which is how many paths of like a certain length you can find in a graph. Yeah, but it's like there's not like one definite way to like tell if a graph is isomorphic to another graph. Sometimes it's easier to like move the graph around and see if you can like
Right.
form. Yeah,
So
because here the last thing I need to do here is I just need to move V3 this way, because once I move V3 this way, I'll basically get this shape, which is basically a pentagon, similar to what's over here. Yeah. But I'll move on to connectivity for now.
So one last thing. So making this star look like a pentagon, that would mean we found a bijection, and since we found a bijection, that's why both of the graphs are isomorphic.
Yeah. So you can find a bijection from this graph to this graph. But in order to do so, what you might have to do is try to rearrange this graph a bit so it looks more like that one. Because the way it is now, even though it looks like the vertices of the star are like in order, they don't follow the same order as this pentagon. Because V1 can't lead you to V2 because there's no edge connecting them. Does that make sense?
I'm sorry, say that again.
So if I want U1 to give me V1, it's hard to tell what U2 is going to be, because maybe you're tempted to say it's going to be V2, but it's likely not V2. It's probably going to be V3 because this is the edge that's connecting it.
Okay, yeah.
Yeah. So it might be good to rearrange it and see if that helps you better. Otherwise, you'd have to go off of like, I start off at one vertex, I check its degree, and make sure that the edge that takes me to the next vertex follows the same rules, basically. You go edge by edge by edge and make sure that all the edges and the degrees kind of make sense.
Right. And what's
Yeah.
a graph invariant again? I know you said it already. That's really
A graph invariant is like any quality of a graph that is preserved by isomorphism. So you can see that this graph and this graph have the same number of vertices and edges. another thing you can observe is that each vertex has a degree of 2, as in there are 2 edges coming out of each vertex. That's also a graph invariant, which is that the degrees of each vertex stay the same. There's another graph invariant, which is that both graphs have to have the same number of paths of a certain length. So a path is basically if I can get to U1 to U3 by these 2 edges form a path.
Right.
Yeah. So a graph invariant is actually, you'll have a cycle, which is basically a path that goes, that starts and ends at the same endpoint. You have to have a cycle of the same length in both graphs. So this one has a cycle of length 5. When you start with the star, you see that this also has a cycle of length 5. So that also gets preserved by isomorphism.
So graph invariants are anything that could like change between all the similarities between 2 isomorphic graphs.
Yeah, so the ones that you learned so far from Rosen are 1, number of vertices and edges, 2, the degrees of each vertex, and the last one is the length of a circuit or a cycle in a graph.
Okay, right.
Yeah. So what topic does everyone want to go over next after this one? I'll just take any answers. Let's see. 32 to 35 from 10.3. Okay, let's see. 32 to 35. What is the sum of the entries in the row of the adjacency matrix for an undirected graph? Okay, so I have to go over what an adjacency matrix is. Let's see. Going back here. So let's say I have an undirected graph. With I'll call this 1, 2, 3, 4. Or actually, I'll start from 0. 0, 1, 2, 3, 4. So the resulting adjacency matrix for this, each row and column of the matrix correspond to a vertex, basically. So for a graph that has 5 vertices, your adjacency matrix will be a 5 by 5 matrix. And basically, if you're in row 0 and column 0, you can order these any way you want, basically. But if you are in a row that represents one vector and a row that represents another vector, you put in 1 if there's a edge connecting them, if they're adjacent to each other. Since there's no loop going from 0 to 0 like this, I just added 1 and now I won't erase. Okay. Since there's no loop connecting 0 to 0, you put 0 here. Since there is an edge connecting 0 to 1, you put a 1 here. 0 to 2, no, nothing. 0 to 3, nothing. 0 to 4, yes. Same here. If there's a edge connecting 1 to 0, you should put a 1 here, even though you already put 1 here, because basically for a simple undirected graph, this is going to be symmetric. So 1 to 1, 0, 1 to 2, yep. 3 to 1, yes. 4 to 1, no. But you basically get the idea of how this works. You just kind of systematically look at your graph, look at the vertices and see, is there an edge connecting them? Then yes. If yes, then just put it in. So what the question is asking is, let me take a screenshot of it. Okay, the question is asking, what is the sum of the entries in a row of the adjacency matrix for an undirected graph? In a row for an undirected graph, sum of the entries, since, oh wait, why did I do that? Okay, since for a row, you're putting down 1 for each edge that is in the graph, you're basically counting all of the vertices that are adjacent to it. So that's the same as the degree of that particular vertex. So that's the answer for the first part. Does that make sense? And then for let's see, okay. And then for
so when we are asking what is the sum of the entries in a row, we can choose one of the rows of 1, 2, 3, 4, and then like count all the adjacencies, like 1, 1, 1.
Yeah. So for any row that you choose, the sum in there should be equal to the degree of that vector. Does that make sense? Because you're trying, it's basically counting the number of edges that connect this vector, I mean, this vertex to another vertex. So it's like counting the degree of the vertex. This is for undirected graphs, but this question is asking it very generally. So the general answer is just, it's counting, it's the sum is equal to the degree of that vertex. For a directed graph, the adjacency matrix looks a bit different. Let me clear this out so you can see. All right, this is trash. Okay, so for a directed graph, let's say I'll make this simpler for myself. 0, 1, 2. There's something going from here to here, here to here, here to here. So 0, 1, 2, 0, 1, 2. Might as well from here to here as well. And here. So what this is asked for the adjacency matrix for a direct graph, you're basically counting the number of edges that take you from this vertex to this vertex, I think. Let me check it real quick. Adjacency matrix. Suleiman, can you confirm real quick? Is it from row to column?
Yeah,
Unless,
row to column.
Okay, so you're counting the number of edges that take you from 0 from the row vertex to the column vertex. So since 0 doesn't go to itself, you can put 0. How many go from 0 to 1? 1. So because this is there is one edge that is directed from 0, which is the initial point, going to 1, which is the terminal point. And how many are going from 0 to 2 here? We're only counting this edge because this is the edge where 0 is the initial and 2 is the terminal. So that's 1. If you have a multi-graph, directed graph, you might have multiple edges that go from one vertex to another, is what's happening. So let's go to the next row. This row, we're counting the number of vertices that take you from 1 to 0, which is just 1. Number of vertices that take you from 1 to 1, 0. Number of vertices that take you from 1 to 2 is also 0. Because you can see in the diagram, while there's an edge that goes from 2 to 1, there's no edge that goes out from 1 into 2. For 2 going to 0, that's 1. 2 going to 1, that's 1, and 2, that's 1. That's 0. So as I said, the number that goes in each row is the number of edges that go out from that vertex. So if the undirected graph, the sum of the entries in the row, we're counting the degree of that vertex. The sum of the entries in a row for a directed graph is actually counting the out degree of that vertex, because you're counting the number of vertices that come out from that vertex. Does that make sense? Okay. Let's see, 33. What is the sum of the entries in a column for an undirected graph? Okay, so the next question is asking not for the rows, but instead for the columns. So I think for the undirected graph, it's the same as the rows for the undirected graph, because the adjacency matrix for undirected graphs are symmetric. So that means you can transpose them and it will stay the same. So that means the sum of the entries for a column of an adjacency matrix for an undirected graph is also counting the degree of that particular vertex. For a directed graph, however, it's different. Directed graphs are not symmetric. So rather than counting the out degree, you're actually coming here, you're counting the number of edges that come into that vertex. So you're counting the in degree for a directed graph. Let's see. Next question, 34. I will screenshot this. Okay, so 34 is asking about incidence matrix. Let me create a new canvas again. So incidence matrices, so these are different from adjacency matrices. Let me draw an example. So another simple 1, 2. So remember earlier when I talked about 2 vertices are adjacent to each other if there's an edge connecting them, and that if you have an edge connecting 2 endpoints, it's incident to those endpoints. So since this is an incidence matrix, this is actually related more to the edges than just the vertices. So let's say I have an edge here. I call this E0. I call this one E1. And I call this one that goes here E2. So for an incidence matrix, my my rows are my vertices. And my columns are actually going to be my edges in my graph. So E0, E1, and E2 for every edge that you have in the graph. So it's basically you put down a 1 if it's incident to that vertex. So that means if that vertex is an endpoint of that edge, you put down a 1. So since E0 is connecting 0 to 2, I put down a 1 here. E1 is connecting 0 to 1. I put down a 1 here. E2 is connecting 0 to 1 as well. So I put down a 1 here. V1, E0 is not incident to V1. So I put down a 0 there. E1 is incident to V1, and E2 is also incident to V1. V2, E0, yep. 0, 0. So if you see something like this, it means that you have multiple edges connecting the same two vertices. That's just a side comment I'm making. So what this question is asking is, what does the sum of the entries here, what does that represent? So if I have, for a vertex, 3 edges that connect it to other undirected graph. Is it a simple one or degree of connectivity, maybe? Okay. So it's basically saying that it's the number of edges that are connecting that are incident to this vertex. I think that might be the answer. I don't see what else it would be. Suyama, do you have any ideas? I think it's just the number of edges that connect that are incident to it.
Yeah, I think it's so good.
Okay. All right. Hope that makes sense.
How did you get the matrix again? Can you go over that one more time?
Oh yeah, of course. So I'll use a different graph. Let's see. So I'll use a graph from the textbook. I'll specifically I'll use the incidence matrix that they use in the textbook. So this is their graph. It's pretty small. Can I make it larger? No? Okay, sure. All right. I'll just zoom in. Is that somewhat visible, or should I zoom in more? I'll zoom in more.
Okay. A little bit, yeah.
Okay, so this is an example they used in the textbook. They labeled the vertices V1 to V5, and they also labeled the edges E1 to E8. You can use any labeling you want. This is just the labeling that they use. It doesn't really matter. How you label it might change how your incidence matrix looks like. But you can label it any way you want, basically. For this, so for an incidence matrix, your rows have to be your vertices. So since the vertices go from V1 to V5, my incidence matrix would let's do that. We'll go from V1 to V5 on the rows. V3, V4, and V5. And then my columns are supposed to be my edges. So you have to label all the edges from E1 to E8 for your columns. Oh, sorry, 3, E4. Okay, this is just the labeling so far. It's not the matrix itself. Okay, so for each index, I put down a 1 if this particular edge is incident to this particular vector. I mean vertex. I keep saying vector. So let's look at the diagram. So E1 is a loop around V1. So that means it is incident to V1 because V1 is its endpoint. So I put down a 1 here. And then I go to E2, V1. E2, V1 is its endpoint here. So I put down a 1 here. E3, V1 is its endpoint as well on the diagram. So I put down a 1.
Wait,
And then we can see that
endpoint or its initial point. They're undirected.
Oh, sorry. Yeah. As endpoint is also used for undirected graphs. As an endpoints of an edge basically represent the vertices at the ends of the edge for an undirected graph.
So
basically if it's a point on that edge, then it's incident to it. That's what an endpoint, being an endpoint on that edge means.
endpoint means like where it starts from, right?
When we're talking about direct graphs, initial point is where it starts from. The terminal point, the terminal vertex or the end vertex is where it ends. But I think they also use endpoint to talk about undirected graphs as well. But when you have an undirected graph, both of them are the endpoints. It's kind of like how when you have a line segment, these 2 points are just the endpoints of the line segment. So that's how I try to think of it. Does that make sense?
Okay, yeah, that makes sense.
Yeah. So on the graph, you just want to look at whether or not it's any endpoint. For an undirected graph, any endpoint is fine. Then it is incident to it. We can see that on the graph, E1 to E3 are the only edges that touch V1. So the rest of it is 0. Yeah. Does that make sense? Or do you want me to do the rest?
Like, can we do one with a directed graph? So like when you're saying endpoints, and I'm like getting confused. With a loop? Like a directed graph with a loop?
A directed graph with a loop. I'm not sure if incidence matrices. Let me think. I think incidence matrices only apply to undirected graphs. As in, you can only do this for an undirected graph. You want me to do an adjacency matrix for a directed graph?
I just wanted to have you're saying that endpoint incidence. So I was like, if what happens if E1 was a loop of
E1 is a
directed
loop.
loop? Yeah, but
Oh
happens
no, incidence matrices like this, they don't apply to directed graphs. So if this,
okay.
yeah, so you don't have to worry about it for a directed graph. Or at least the textbook only talks about it in terms of undirected graphs. Yeah. And any more questions?
No, I think I got the idea of incidence graphs.
Okay. I think I have time to go over one last concept. You guys can choose it.
Did you solve 32 to 35? We did
Let me
32.
see. I did. I did not do 35, which is just talking about the columns. Let's see.
So
I'll
for
just do it for
30
one.
So for 32, we said the rows of an adjacency matrix in an undirected graph is the degrees, and for a directed graph is the out like the
Out degree. Yeah.
out degree, and for the columns of the matrix is same thing. It's the degree of undirected and the in degree, or for and
Or
then for
a directed graph.
undirected it's an in degree.
Yeah, in degree.
How is it in degree again?
Because I'm not drawing another adjacency matrix, but I'll
Yeah,
just
yeah.
find the one in the textbook and look at that. Okay. This is no. This is the adjacency matrix. Yeah. Where's the directed one? Do they not have a directed one? Wow. No, they should have one. Oh well. For some reason the textbook doesn't have one for a directed graph. But they do exist. They just don't have a diagram for it. But basically, the columns
Right.
for adjacency matrix just represent the vertex that the edge is going into. So that's the in degree.
Okay.
Yeah.
And then so that was 32, 33, and then 34 said the sum of the entries of the row of an incident matrix for an undirected graph, we said is the what again?
It's just a number of edges incident to that vertex.
Okay, and then the sum of the entries in a column of the incident matrix for an undirected graph is same thing, the number of edges.
The
No,
number of edges.
I think that would be the number of
It should always be
vertices.
two. It should always be two.
Because every vertex, because the columns represent the vertex, so every
The
vertex
columns
should
represent
have
the edges.
uh
Yeah, the columns of an incidence matrix
oh
represent
yeah,
the
yeah, they
edges.
represent the
Yeah.
edges, so every edge should have two vertices.
Yeah.
Okay, makes sense.
All right. Any last questions that we want to go over? I think we have like 10 more minutes since I started late. So, Iman, you want to take over?
Well, I think there's not much else stuff to cover.
You should go over vertex connectivity
Vertex connectivity. Okay.
and vertex cuts. You remember those? Did Professor Kong go over vertex connectivity and vertex cuts?
We started to do it a little bit on our last class, like only one slide. We talked about like connectivity, paths, and circuits.
Okay. Did he mention, I think that might be on the exam, or?
Yeah,
I
he
think
said
maybe
it's gonna be
understood.
on the exam, yeah.
Yeah.
Okay.
Yeah.
Tatyung, you want to take over?
Sure.
Good
So what
job.
section are we
Thank you.
doing? 10.4,
10.4.
right?
Yeah. If you go to 10.4.4, that should be good. I'll stop sharing.
Mhm. Okay, oh, this isn't bad.
Here. Yeah.
So basically, what was that, Kathy?
I just said yeah.
I mean, okay, so connecting this in a graph is like, so in a graph, when you have edges and like nodes between that, when you have nodes and the edges between them, what you can end up with is different components of a graph. So like say in this example, we can say this is an entire graph right here. Entire graph is G. This graph has three separate components, right? So this is G1. Here they have G1, G2. I'm just gonna label this as G2. This is G3, right? Same here. So we have a graph H. Basically, connected to components is anything that's like any graph where you could get to any like node within that graph, right? So I can go from B to A. Even if I take out this edge, I can still go from B to A. I just have to B to C. I can just have to go through A. Right, same thing here. So F, H, G. I can go from H to F. I just gotta go through G. Right? And then when it comes to like vertex cuts, right? Basically, if I gave you a graph, right, let's say G1, the minimum number of like edge cuts is, say I take away this. See, right now it's just one graph because I can go from any point to any other point. Right when I take away this edge, right, now it becomes two distinct graphs. I can't go from C to E, and thus I can't go from anywhere in this graph to this graph. Okay, so the minimum number of edges in this scenario to make this graph disconnected is just one. I remove one edge and it's disconnected. And you don't need to only remove edges, you could also remove nodes. Right, so say if I remove the node C, I take this node out, that means all the edges that are connected with C are also gone. And thus this becomes ABD and FEGH. Okay. Is everyone okay with that concept?
Yes.
So if we look at this example right here, the minimum number of edges I'll have to remove in order to make this graph disconnected, it has to be 2. Minimum 2. If I remove this one, right, you could still go from B to, say, D through A and C. I have to remove 2, right? So the minimum number of edges to make this graph disconnected is 2. Whereas the minimum number of nodes or vertices to remove is 1. If I remove C, which is like a pinch point right here, because everything has to go through C in order to get here, right? Once I remove C, you can't go from A or B to D, E, or F. Okay. Let's see if there's any examples. Vertex connectivity, connected. Okay.
I think those were the examples they gave.
I'm saying like we went over isomorphic. Practice code. Okay. These list the vertices from a path in the following with graphs are simple. Do each of the lists of vertices form a path in the following graph? Which paths are simple? Which circuits? Circuits, I think, are just you could go from the start to the end. So this is a circuit right here. What's that with E, B, A. So you start at E, you go to B, you can't go to A. It's annoying. So this isn't. I can't do that. This one is. You can go from A to E to A to D to B to C to what the hell are these circuits?
Maybe D. Maybe D is a circuit.
Maybe D. Basically, the circuit is you start and you end at the same point. That's the whole idea of it, right? So you start and you end at the same point. So we start at C, we go to B, we go to D, we go to A, we go to E, we go to C. Yep, this is a circuit. This is a circuit. Okay, another circuit that could be from this graph is you start at C, you go to E, you go to B, you go to C. Okay. Yeah. Vertices. Okay, so then once you add direction, then it switches it up a bit. So let's see this again.
I just wanted to ask, if I was ADA, that's a circuit?
ADA, yeah, that's a circuit.
Yeah, it's a circuit. It's not a simple circuit because you're taking the same path twice. So that's like another definition. Yeah.
Yeah, simple circuit. I think they go into this more when they go into like Hamiltonian paths and such.
Mm-hmm.
But like in this example D, in the example of a simple circuit, once you use an edge, you can't use it anymore. I think that's more to the Hamiltonian circuits. So you start at C, you go to B, and B to D, D to A to E, E to C. So this is a Hamiltonian circuit. In this case, Hamiltonian circuits is you go through, and once you use an edge, you can't use it anymore. Once you use it, you lose it. Right? So hitting every edge once. I think actually here we don't actually need this edge. So we don't even use this edge. Ignore it. But yeah. But to answer your question for Korea, yeah, A to D, D to A. It's a circuit technically, but since we use the same edge twice, it's not really a simple or Hamiltonian circuit. So now once we add direction, changes it up a bit. So let's say this one. Let's say now let's think this one. So A to B, B to E, E to C, C to B, B to D can't go over. What the hell? Okay. A D, no. A B E C B. Well, let's look at A. So A B E C B. So this portion, the B E C B, this is a cycle. Cycle. Okay. And it's not the entire thing isn't a cycle because remember, a cycle has to start and end the same point. A D. This is also a cycle, but it's not a simple cycle, but a cycle circuit because it uses the same edge twice, AD and AD. But here we have BECB. BECB is a cycle because you go into a circuit path. So here you go. It's literally the same concept, but whereas in this graph you can go in either direction with the edge, this graph the direction is like it's written out. So in essence, these two edges right here in directed graphs is the same as this edge right here in the undirected graph. Okay. Any questions? Does anyone have any other topics they want to go over? I feel like your exam's gonna be entirely graphs, which is really weird for 220 because 220 isn't supposed to be all graphs, but I guess Khan has his ways. Anyone have any other questions?
Did you guys go over logic or?
Look, I'm looking at their syllabus and it's literally graphs, 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 graphs. This vertex color is just graphs. And then they briefly go over relations.
Interesting.
He doesn't even teach it. He makes you read like big O notation, which I don't know why. That's weird. Like he should really teach big O notation, but I guess whatever. You guys better be good at graphs, so then you go into 313 after this. Any other questions?
No, all good. Thank you
Thank you.
for waking up Saturday morning to help us out. Appreciate it.
No,
worries.
if you could get go over the Hall's theorem a little bit. It was like really I couldn't, how do I say it? The Hall's theorem was really not
Yeah, it's a
uh
hard one.
it was too
Which section is Hall's theorem again?
10.2. But yeah, before you guys go, make sure to fill out the feedback form. That helps keep these sessions going. But we'll like try to explain Hall's marriage theorem
think
one
that-
last time.
Hall's theorem is a bit more. It's weird because that's more like stable marriage. Okay, marriages on islands.
So you have a complete bipartite graph.
The bipartite graph with a bipartition V1, V2 has complete matching from V1, V2. If and only if n of A is greater than or equal to absolute value A for all subsets of A of V1. It's hilarious how in CS you can just create a random theorem and become so famous from it, but let's see. It's the most random of theorems. Marriage theorem. Anyways. So I think what it's saying is if you have a bipartite graph, right? So you could split it into two subgraphs where everything in this first V1 is connected with something in V2. Okay. And nothing in V1 is connected with itself, nothing in V2 is connected with itself. Okay. It has a complete matching from V1 to V2. If and only if all subsets of A. So I'm assuming n of A is in, okay, so for any given amount of nodes from V1, so if I choose any amount of nodes in V1, any subset of in V1, it has a complete matching from V1 to V2. Okay, I think, so basically what it's saying is regardless of however many men I choose, they all have, like it's basically, how do I word this? Each of these men has like a preference, like they're willing to marry some woman, right? So that function, let's say it's called like a willingness to marry someone. Willingness. Right? The idea is, regardless of however many men I choose in this as a subset from V1, the number of women they're willing to marry has to be greater than or equal to the number of men I've chosen.
No, I was just yeah, I was just confused in the bipyrate graph. When we say this is a bipyrate graph, we are saying that all the vertices on V1 has a connection, has one or more connection to V2, but not all V2 vertices has connection with V1, but it's still a bipyrate, right?
For this one's for bipartite graphs, yeah,
Yes.
basically you're only allowed edges that connect V1 to V2, but not V1 to itself and not V2 to itself.
Yeah, but I'm saying that like suppose there are like 3 vertices on V1 and like 10 vertices on V2, and there is like only one edge from V1 to V2 for each vertex of V1. So there's only 3 edges. So
Sorry.
every vertex on V1 is connected to one of the one of the vertices on V2, but not all vertices in V2 is connected to edge vertex of V1. So there's still a bipyrate, right?
Yeah, it is.
Complete
It is.
bipartite means everything is connected, but bipartite means you can split it into two two separate graphs where everything in V1, well, nothing in V1 is connected with each other, or nothing in V2 is connected with each other, and there exists connections between V1 and V2 nodes.
But not all V1 vertices and not all V2 vertices has to be connected, right? Or
Yeah,
is it only
there could be a V2 here that isn't connected with anything.
with anything? Okay, that's a bipyrate graph.
That's
But
my part.
no, I'm saying that what happens if there's some vertices in V1 that's not connected to anything.
Like this?
And yeah, and there's some vertices in V2 that's not connected to anything. Those are still bipyrate?
Yes, by definition of bipartite, yeah. But complete for Hall's theorem, I think it has to be complete.
Okay, so for a complete bipartite, one of the V1 or V2 has to have all the vertices that has to have edges, right?
Yes.
Okay. And for there was another bipartite. What was it called? The partite that has like all the vertices in V1 and all the vertices V2 are meshed.
That might be the complete one.
I think that's complete.
No, no. Complete is one of the vertices. One of the V1 is all the vertices in V1 is matched to one of the vertices on V2.
Complete has to be.
Is it like a full bipartite or something? Or maximum matching?
Yeah, I think that's it. Max, maybe. Bipartite. Yeah, it has to be max.
So maximum, what's the difference between a maximum matching and a complete matching?
Hold on, let me read this.
I see. Maximum matching basically means you just want to get as many edges as possible out.
I have three. Oh, sorry, Kathy. I'm just gonna draw.
No, you can continue. Sorry.
A maximum matching is something like this. This is connected with this. Everything is connected with everything else. Like this. Right here. Right here. Right here. You have all the possible edges we've made, and it's still bipartite because nothing in this is V1. This is V2. Nothing within V1 is connected with each other. Nothing in V2 is connected with each other. This is a maximum matching. A complete
maximum matching is all the vertices in V1 has to be connected with all the vertices in V2?
Yes.
That's just okay.
Complete matching means no one's left alone. Right here, this could be like this, like this. This is an example of a complete matching. Everything in V1 has at least one in V2. So you don't have like an edge here that has nothing in it, right? That could be something like this. Complete matching. Okay.
This is a complete matching from V1 to V2?
If I'm not mistaken, yeah.
But this is not a complete matching from V2 to V1 because there is 4 and 3, right?
Complete matching from V1 to V2 if every vertex in V1 is the endpoint. I think it only matters from V1, as in the number of edges in the graph has to be equal to the number of edges that come out of V1.
Mm-hmm.
So that's a complete matching. So this would not be a complete matching because you have one too many edges.
Oh, sorry. One sec. This one could.
So this would be a complete matching from V1 to V2, but not from V2 to V1 because you have too many edges for it to be a complete matching from V2 to V1.
No, isn't it? This is a complete matching from V2 to V1, right?
This is
Because
a
like
complete matching from
V1 to
V1 to
V2.
V2.
We have 4 edges, 1, 2, 3, 4, and 4 nodes in V1. But not from V2 to V1 because there's 4 edges with 3 nodes in V2. Okay.
okay.
Does anyone else have any questions? If that's it, I think we're good to go.
Yeah, the recording will be up by Monday, hopefully. We'll send an announcement. We'll have it also on our resources page on the Learning Commons.
Pull up the
And we'll also post it on Code for All too.
Have a good day.
You too.
So if you want to look where it is, resources, computer science, it should be under here. 220. It'll be here. Yeah.
All right. Thank you.
Thank you all.